Hey again, everybody. Thanks for watching another video clip. Yeah, you're ambitious. This is some extra practice with regards to the technique called method of initial rates for determining the order of a chemical reaction. I think we've seen a couple of these already, but maybe this is your first one. So in this hypothetical situation, looks like I have reactants A, B, and C. Perhaps it'll be a slow reaction because three reactants come in together at one time. It takes time. It's kind of a slower process often. Looks like the experimenters had four trials. They had reactants A, B, and C, and they measured the rate of the reaction in the very beginning. Sometimes the scientific notation can confuse some folks, so I might just dispense with it or remind how to change from scientific notation to regular decimal form. But I see concentrations and rates, etc. for four different trials. Do you see two trials that might hold something constant, one or two of the reactants constant, but change the third? And from that we can observe how the rate changes. Look at trials 1 and 2. In trials 1 and 2, my A stays the same, my B stays the same concentration, molar concentration. My C doubles from 0.11 to 0.22, resulting in what happens to the rate? Oh, I see. This is 0.0008. This is 0.0016. If you look at the times 10 to the negative 4 times 10 to the negative 3 part. And so, in other words, this also doubles. Double 8 and you get 16. Let me write that out. Comparing trials 1 and 2, my A and my B are held constant. So my A is constant, my B is constant, my C doubles, resulting in the rate also doubling from 0.008 to 0.0016. Therefore, since the same thing happens to C, the rate happens to C, I say it's first order in C. I can write more of that out later. But it seems like I didn't need trials 3 and 4, but I certainly might need them in trying to figure out B and C. Alright, let me see. Is there a place where I hold C constant? Oh, look, trial 1 and 3 I hold C constant. Oh, my goodness. Let me pause for a second. So, sorry about that. I hold in trials 1 and 2, I hold C constant at 0.11 and B constant at 0.11, and my A goes from 0.11 to 0.44. That's a quadrupling in the A, from 0.11 to 0.44. Question, does this also quadruple? Does the rate quadruple from 0.0008? Multiply it times 4, indeed you get 0.0032. So yes, since the same thing happens to the rate multiplicatively speaking, the same thing happens to the rate as happens to the concentration, and the others are held constant at 0.11 and 0.11, then it's also first order in A. Let me write that out. Considering trials 1 and 3, I held B and C constant, while A quadrupled, resulting in the rate also quadrupling. Sorry, that's terrible English. It's a run-on sentence, but I use it anyway. Okay, so that's a thinker, but the same thing happens to the rate as happens to the concentration over here, holding everything else constant. Tells me that it's first order in A as well. Alright, let's look at one more. We got to figure the C out. No, I'm sorry, the B. We've determined it's first order in C, first order in A. Look at trials 1 and 4. Trials 1 and 4 hold A constant and C constant, and B triples from 0.11 to 0.13. Question, does the rate also triple? Oh goodness, triple times 8 would be 24, so no, it does more than that. So in trials 1 and 2, A and C are held constant, B triples, resulting in the rate multiplying times 9. 9 times 8 is 81. And so how does the 9 relate to the tripling of the B concentration? The answer is it's tripled to the squared power. 3 squared is 9. Our next example might shed a little bit more light on a different way to look at that, but it's indeed second order in B. So putting all that together, I write a big rate law, and I go about figuring out k. The rate equals some constant k, a to the first, c to the first, b to the second. You don't have to write the ones up there, but I do when I'm first describing the order of the reaction. And I took data from trial 1, the rate, the molarity of A and B and C. You'll notice B is squared. And unless I made a mistake, which I don't think I did, this all works out to 5.5 for K, and the units are funky. Got 3 molarities here, 1 molarity over there. One of those, this molarity cancels one of these molarities. And indeed, the units 1 over molarity squared seconds. So if I were to write it out, including the constant. So again, the power of this is I could use any reasonable concentrations for A or B or C, which I've never tried before, plug them into this newly discovered rate law for this particular temperature, and theoretically anyway, I could discover the rate of that reaction for those concentrations, never having tried it before. Let me try one more. Here's a reaction between a gas, call it X, and another gas, call it Y, X and Y. Some coefficients in front, M and N, I don't know. They could be ones. I don't even know what they go to. I don't even know what they produce as products. But I don't have to. As long as I have some data that describes how one of them might change holding the other constant. In this, I'm looking at gases, so I can measure it in pressure. Pressure in torr, time in seconds. Trial 1, 2, 3. In trial 1, 200 and 200 partial pressure of X and Y resulted in a rate of 50 torr per second. 400, 200 result in this rate. 600, 400 result in this rate. If you feel brave, pause the video and see if you could figure out the order of the reaction with regards to the pressure of X and or the pressure of Y. Alrighty then. Let's see if I can figure it out. Here in trials 1 and 2, I hold the pressure of Y constant, but double the pressure of X, 200 to 400. So if this one doubles, this one stays the same. Does this also double from 50 to 100? Yep, sure enough. Double 50, you get 100. So I'm going to go first order in X. And I wrote that right here. Trials 1 and 2, the pressure of Y is held constant. The pressure of X doubles along with the rate, also timesing by 2. Therefore, it's first order in the pressure of X. I could write this. The rate with respect to X is equal to some constant, although that's a pseudo constant. It's not the overall constant because I'm not including the Y yet. Pressure of X to the first power. The next one's going to be a little bit trickier because my silly experimenters, the people that did the experiment, didn't think far ahead enough to hold the pressure of X constant. So as to allow me to find am I saying this correctly? Yes, they didn't hold the pressure of X constant. They varied or I don't have enough data. So, but you know what I can do? I can look at this and say, even though I don't have a place where I hold X constant to decide the power or the order with respect to Y, I can still use my knowledge I found above to say this. In trial 2, this will work. In trial 2, I could say this. So my rate has got to equal my pressure of X to the first power times my pressure of Y to the I don't know what power. There's some constant thrown in there. Rate 3 right here should equal to the pressure of X to the first power times the pressure of Y to the I don't know what power. This px looks like this, and this py looks like this, and this px looks like this, and this py looks like this. So you got to be careful on what you're filling in there. But those two equations look like this. This question mark and this question mark are indeed the same question marks, the same unknowns. And I have two equations and one unknown. It should be pretty simple to solve for. Since both of these equations must be valid, I could equate them like this in a ratio, or I can pull them apart a little bit. Mathematically, this is still kosher, but I don't know what this question mark is. But let me simplify a little bit. 100 over 600, 400 over 600, this is both to the first power. The k's cancel, k over k cancels. But this question mark and this question mark could be brought together. So in other words, I have this. And remember this. So the zeros cancel. The k's cancel. These zeros cancel. 4 over 6, 1 over 6, 2 over 4 to the question mark. Let me bring this 6 over to here, this 4 down to here. 2 over 4 is equal to 1 half. So this goes to this. The 6's cancel. And I have 1 over 4 equals 1 half to the what power? And is it obvious? It's a 2. I'm not going to, forgive me if I don't solve that rigorously mathematically, but 1 half to the what power gives you 1/4. Yeah, it's 2. So in other words, we are second order in the pressure of Y. We've discovered what that question mark should be. So finally, I could use, say, trial 1 data and my newly discovered rate law to plug and chug. 50 for the rate, 200 for this pressure, 200 for this pressure. We just discovered a second ago that this was second order with regards to the pressure in Y. And so I take 200 there, 200 there, square this one. Torr squared times another torr to the cubed, 50 torr per second, keeping track of my units, comes out to a small constant. 3 torr down there, 1 torr up there. Final answer for the rate law. I think that's it. Yeah. Well, if I made a mistake here, I'm sure you'll let me know, but feel free to ask questions, and I'll see you soon. Thanks, guys.